December 1963 marked a critical moment in the history of Soviet nuclear engineering. Hidden deep inside the Siberian wilderness, Soviet engineers were confronted with an unprecedented challenge: the commissioning of the AD-2 reactor, a formidable, graphite-moderated nuclear furnace built to produce plutonium for atomic weapons. The reactor was to generate an extraordinary 1,450 megawatts of thermal power, enough to vaporize a small lake within minutes. Yet, this massive reactor was not built in a traditional setting. It was embedded deep inside a mountain. Unlike conventional facilities that had access to the open air and external cooling systems, this facility was trapped beneath 200 meters of solid rock. Conventional methods of cooling large cooling towers and exposure to the atmosphere were impossible here. With no access to the open air, the cooling process had to be reimagined entirely. The surrounding environment added another layer of complexity. The temperature in Siberia during the winter could drop to a bone-chilling -40 degrees Celsius, freezing the Yanis River, the nearest water source. The river was one of the mightiest in Siberia, but in this frozen, isolated environment, it offered little help in cooling a reactor that could produce intense fission heat. Even with the river flowing, ice jams formed in the winter, reducing its flow rate by nearly 70%. This, combined with fluctuating temperatures that ranged from near freezing to temperatures upwards of 14 degrees Celsius during the summer, made it a logistical nightmare for engineers tasked with designing an effective cooling system. In 1950, at the height of the Cold War, the Soviet Union was in the midst of a nuclear arms race with the United States. The U.S. had already demonstrated the destructive power of atomic bombs with the detonation of bombs over Japan in 1945. By 1949, the Americans had amassed a considerable nuclear arsenal. In contrast, the Soviet Union was still behind, having only detonated its first atomic bomb, RDS-1, in August 1949. Despite the progress, the Soviets were still playing catch-up in terms of nuclear capability. Under the tight grip of Joseph Stalin and the leadership of Lavrenti Beria, the Soviet nuclear program aimed to match the U.S. in nuclear weapons production. In a highly secretive operation, the Soviets decided to build a plutonium production facility deep in Siberia, away from the reach of American bombers. The selected location, near the Yanis River and approximately 50 kilometers northeast of Krasnoyarsk, was ideal for its remote location, natural resources, and the geological characteristics that allowed for the construction of an underground facility. The location was given the highly confidential name, Krasnoyarsk 26. It remained hidden from the public eye, even on maps, and was accessible only through a postal code connected to Krasnoyarsk. To keep the project secret, the workers, approximately 70,000 individuals between 1,950 and 1,964, were not volunteers, but political prisoners, forced laborers, and members of the Gulag system. These workers were tasked with building the complex from scratch. They drilled, blasted, and excavated tunnels using primitive tools, all while enduring brutal conditions. The death toll from these efforts was never officially disclosed, but the hardships and human cost were undeniable. The first reactor at Krasnoyarsk 26, the AD reactor, was commissioned on the 25th of August 1958. Following this, the AD-1 reactor came online in July 1961. However, the engineering solutions employed for cooling these early reactors were far from perfect. To solve the immediate issue of cooling, the engineers resorted to a simple yet environmentally disastrous solution. They pumped water directly from the Yanis River, ran it through the reactor core once, and dumped the heated radioactive water back into the river. While this solution allowed the reactors to function, it came with severe consequences. The radioactive water tainted the river, and downstream villages began reporting mysterious illnesses. As the power output of the reactors increased, it became clear that this solution was unsustainable. Environmental concerns mounted, and it was evident that a more sophisticated cooling system was needed. Thus, the AD-2 reactor was designed to address both the engineering and environmental challenges. The engineers were tasked with developing a cooling system that would not only prevent contamination of the Yanis River, but also provide district heating for a growing secret city of 70,000 people. The design of this reactor would set the stage for what would later be considered one of the most innovative cooling systems in nuclear reactor history. The AD-2 reactor's design incorporated several revolutionary features that had never been attempted before. The core of the reactor consisted of 2,832 vertical fuel channels, each lined with aluminum and containing uranium fuel rods. Each fuel element was capable of producing 10 kilowatts of thermal energy. The reactor's total thermal power output was a staggering 1,450 megawatts, comparable to a large commercial power plant, all contained in a compact underground space. To effectively cool such a powerful reactor, Soviet engineers faced multiple challenges. First, they needed to ensure that the cooling system could maintain a constant, safe temperature despite the extreme environmental conditions and underground location. The typical cooling towers used in commercial reactors were not an option. Second, the cooling system had to be efficient and effective under varying conditions, freezing temperatures during the winter and the increased flow and temperature of the river during the summer. The solution lay in the development of a closed-loop cooling system that could operate year-round, maintaining temperature regulation and keeping the reactor at a safe operating temperature without depending on the river. The key innovation was the creation of a dual cooling circuit design, which separated the primary and secondary cooling systems into two independent circuits. In the primary circuit, high-pressure water was pumped through the reactor's fuel channels. This water absorbed heat from the uranium fuel rods and became radioactive. The critical feature of this primary cooling loop was that it remained completely isolated from the environment. This water was pumped back into the reactor after being cooled through a heat exchanger system. The secondary cooling system utilized the heated water from the primary loop to generate steam for both electricity production and district heating. The hot primary coolant transferred its heat to the secondary circuit, which used this heat to produce high-pressure steam. This steam then powered turbines that generated electricity for the reactor and the secret city. The remaining heat was fed into the district heating system to provide warmth during the harsh Siberian winters. The challenges of maintaining such an intricate system were immense. The engineers had to contend with fluctuating river temperatures, seasonal water flow changes, and the unpredictable effects of freezing temperatures on the reactor's cooling systems. However, the engineers at Krasnoyarsk 2-6 also designed an innovative intake system that could adjust to the changing river conditions. They built a multi-stage water treatment facility to remove debris, ice chunks, and sediment from the river water. This facility, located underground, ensured that the water entering the cooling system was clean and free from contaminants. The water was then treated with chemicals to prevent corrosion in the aluminum-clad fuel rods and to ensure the reactor's longevity. This clever use of water treatment dramatically reduced the frequency of coolant leaks and prolonged the life of the reactor's components. Additionally, the graphite moderator within the reactor generated its own heat. The engineers designed a separate cooling system for the graphite core, using nitrogen gas to carry heat away from the core. Nitrogen was ideal because it didn't react with the graphite, preventing dangerous oxidation. The nitrogen was circulated through the core and cooled before being returned, further protecting the reactor from overheating. The AD-2 reactor was a success. It began operating in 1964, and over the decades, it provided a reliable source of plutonium for nuclear weapons production. More importantly, it supplied the vast majority of heat and electricity for the city of Krasnoyarsk 2-6, which had grown to a population of nearly 100,000 by the 1992. However, after the collapse of the Soviet Union and the end of the Cold War, the AD-2 reactor's mission changed. It ceased to be a weapons production facility and became a purely civilian power plant. Despite growing concerns about its aging infrastructure and the increasing international pressure to shut it down, the reactor continued to operate because of its vital role in heating and powering the city. In the 1990 seconds, Russia and the United States entered into negotiations to replace the AD-2 reactor with a fossil fuel-based system. After years of delays, the reactor was finally shut down in 2010, ending an era of remarkable engineering achievements. The legacy of the AD-2 reactor, however, lives on in modern nuclear reactor designs. The principles pioneered at Krasnoyarsk 2-6 influenced the design of pressurized water reactors used worldwide today. Chapter 7. Final Reflections. The AD-2 reactor at Krasnoyarsk 2-6 stood as a testament to the ingenuity and determination of Soviet engineers. Operating in an environment where few thought it possible, the reactor was a symbol of both Soviet ambition and the lengths the country was willing to go to in its pursuit of nuclear power. The engineers overcame enormous challenges, from sub-zero temperatures and complex cooling systems to managing the delicate balance between plutonium production and civilian needs. While the environmental and human costs of the reactor's construction were high, the AD-2 reactor remains an extraordinary feat of engineering. It provided a lasting lesson in how to meet seemingly impossible challenges with resourcefulness, innovation, and sheer determination.